Hi everyone, my name is Lokman Salamatian, and today I will present our research on applying Riemannian geometry to internet measurements of private backbone infrastructures. Let me start with an observation. Cloud providers have been heavily investing billions of dollars in their backbone. This is a process that started a decade ago at the time where a huge portion of the traffic was headed toward a few large content delivery networks. In 2017, for example, Google was carrying up to 25% of the whole internet traffic, and this fraction has probably increased since then. The increased premium from unhappy transit provider who had the responsibility to invest heavily in the physical infrastructure, combined with the dependency to best effort internet, led cloud providers to build their own backbone network separated from the rest of the internet. Our first question in this project is to understand the physical topology resulting from those heavy investments. While I'm talking about cloud provider, it is important to note that they each are a unique entity. Before being cloud providers, each of those enterprises, namely Amazon, Google, and Microsoft, were playing a different role in the network. Therefore, the newer infrastructure is conditioned by their pre-existing historical deployment that reflects their past role. On a higher level, although they might be competing for similar markets nowadays, each of the company had unique strategies and different goals to begin with. So a valid question we can ask is, how did their network evolve uniquely, even though their objective might be overlapping now? Both questions are not necessarily new questions and can be answered through measurement. So how did we use to answer those questions in the past? The traditional approach when it comes to geographic mapping of infrastructure consists of first scheduling traceroute measurement, then applying heuristics to obtain router level interconnectivity, and to finally geolocate routers through reverse DNS hints in order to generate a physical topology. This technique was formalized more than 20 years ago in rocket fuel. At first sight, it could seem like the problem is already solved. However, the basic mechanism used by traceroute is unable to detect the utilization of layer 2 technology, such as MPLS, and cloud providers are known to configure the network through various tunnels. Secondly, the rise in deployed middle boxes such as firewalls, NAT, proxy, and deep packet inspection boxes across the internet results in obscuring the topology further. In a deeper sense, this trend of obfuscation of traceroute output is likely to remain and accelerate. And while there have been really interesting research to extend traceroute to address some of the challenges, their deployment can be tricky, and an expected evolution of the network might result in further obfuscations. In this work, we wanted to take a principled approach on what we believe would always be accessible through internet measurement. In the bottom line, we believe that when one considers the sort of measurements that necessarily must be available to a third-party researcher, it becomes clear that only end-to-end measurements are guaranteed to be available. Of these, the simplest is end-to-end round-trip time. Furthermore, it is generally possible to obtain at least approximate geolocation information about end systems. We're now ready to state our three primary goals in this project. First, we want to get a clear view of hardly observable topologies that play a central role on the internet. Secondly, we want to compare and contrast different network properties of the different cloud providers. Thirdly, we would like to build alternative internet measurements that are easily deployable, generate probe packets that are not susceptible to be tempered by third party, and yield high-quality end-to-end information that can be compared to a properly executed traceroute probe. Let's assume that we start with a couple of devices that can schedule simple measurements. We also assume that we know where they're located. We'd like to discover the underlying fiber connectivity between those points. This means understanding how the different points are connected with each other. Starting from delay measurement and geolocation, we envision to model the measurement between 2 points as being samples from a hidden underlying space that we're trying to recover. Our hope is that this space can be approximated by a manifold on which shortest path between points indicate network latency between end systems. This representation permits to move complexity away from the measurement component to the modeling component. Concretely, this means that we create a methodology that provides a meaning for learning this manifold, that is, uncovering the geometry of this unknown space. In particular, the data points represent shortest path along the manifold surface that encode a composite view of underlying physical network infrastructure. The second idea is to leverage the fact that points on the internet have geographic coordinate and that geography strongly informs the manifold shape. We can therefore learn a manifold that satisfies the constraint induced by geography as well. Now that the idea have been clearly stated, we can move on to the methodology. Our methodology is decomposed into 5 main steps. The first step is the measurement component. We schedule ping measurements from geographically distributed vantage points in the space. We first lower bound the observed latency using the notion of deterministic latency. Assuming that there exists a direct straight link between 2 points, refraction tells us that the speed in fiber is at most 2/3 of the speed of light in vacuum. We can define the deterministic latency as a latency induced by physical constraint on an optimal cable. Now that we have defined the deterministic latency, we can also define a residual latency. The residual latency is the difference between the observed latency and the deterministic latency. We can explain the residual latency through several factors, such as queuing delays, transmission delay, traffic engineering, absence of trace path, and so on. When we sample the observed latency over a large period of time and select the minimum observed latency, we can minimize queuing delays, transmission delay, traffic engineering effects to observe the real shortest latency between 2 vantage points. In our work, we select the 1th percentile on a sample over a span of 2 weeks as it provides a more robust statistic. Let us extend our previous example by assuming that we have now 9 fixed vantage points across the network. They're in different locations, and we can again schedule ping measurement between the vantage points. We assume that we have a few missing entries, which is often true in practice. In our figure, we bolden the line that corresponds to the real physical fiber connecting the points. We're interested in recovering that information from our measurement. We define the distance matrix as the remaining latency between 2 vantage points. We build and investigate the residual latency CDF. The x-axis corresponds to the residual latency, and the y-axis quantifies the fraction of the matrix that has a residual latency smaller than a given x. For example, when x is equal to 30, 45% of the entry of the matrix are smaller or equal to 30. We can, for a given x, build a graph such that 2 nodes are connected only if their residual latency is smaller than the selected x. We take as example 2 thresholds, 30 and 80. On the small threshold, we notice that we have only local links. Those intuitively corresponds to islands of local connectivity. At a higher threshold, we're able to recover the true physical topology. This time, the different islands of connectivity are merging into a single connected component through the addition of a couple of new edges. We would like to design an automatic technique to detect the right threshold at which we have discovered important features of the topology. Our desired technique should be scale invariant in the sense that it should be able to detect edges at different granularity, robust to noise, and allow for an intuitive explanation. Before diving deeper into the metric that we select to signal important discoveries of the topology, I would like to make a brief interlude into a fairly intuitive yet mysterious geometrical concept, the curvature. The curvature intuitively measures the volume distortion on balls of small radius on the manifold from the same balls of identical radius on a standard Euclidean space. There exists many other interpretations, and curvature is a fascinating area of research in its own right. In our case, we adopt Yann Olivier's interpretation of Ricci curvature based on Earth mover distance. The main idea in that context is to define Ricci curvature as a property that encapsulates how strongly connected the neighbors of the endpoints of an edge are. The exact detail on how to compute the Ricci curvature can be found in the paper. I want to emphasize the intuition for now. There exist 3 archetypical curvatures. Negatively curved space can be modeled through saddles. In the discrete case, negatively curved edges corresponds to edges that attract a lot of traffic when moving from the neighbors of F to the neighbor of H. In neutral curvature, moving from the neighbor of H to the neighbor of F can be done directly without relying on FH. All the edges carry a similar amount of traffic and shortest paths are direct. The third and final type of curvature is positively curved geometry. In that context, F and H share the same neighbor, so moving from one distribution of neighbor to another requires almost no work. In that geometry, all the shortest path travels along converging lines. Getting back to our previous plot, we are able to identify that negative Ricci curvature of an edge indicates when new important bridges of connectivity have arisen. To automate this process, we take every graph generated for different thresholds and compute their distribution of Ricci curvature. We then leverage each of those distributions to generate a single box plot and identify threshold where new important links have emerged in the structure. To supplement the box plot and understand where important connectivity has arisen and the scale at which that connectivity appear, we build emergence plot heat maps. The idea of those plots is to represent the first threshold at which the edges have emerged in our structure and their associated Ricci curvature. Finally, we can look at how the different isolated vantage points percolate to become a single connected component through the Sankey diagram. As we were discussing earlier, Ricci curvature is originally defined in continuous sitting. And so we spent a considerable amount of time to translate back the discrete view to a continuous representation. We build manifold representation of the graph that preserves curvature information. In this example, we note that the manifold representation preserves physical topology such that the shortest path from J to A follow the structure constrained by the physical topology. We can generate such manifold for each threshold, but we'll specifically focus on the threshold where negative curved edges appear for the first time. We move away from the idealized example introduced in the previous section onto real deployment with real data. We deploy virtual machines in the different cloud and collect RTT measurement using both the public and the private IP addresses. The exact details of the measurement can be found in the paper. We focus on Asia for our case study. We reiterate the same analysis as the one described in the methodology section. We first generate the Ricci curvature box plot. We observe that the first negative edge appears at a threshold of 60. The most negative edge is at a threshold 90. We also consider the threshold 30 to illustrate how local connectivity occurs, and threshold 120 to observe the properties of our manifold for higher thresholds. As performed earlier, we build our graphs and note localized structure on smaller thresholds and bridges of connectivity appearing at higher thresholds. We only investigate the graph C in the manifold representation D in this presentation. Detailed description of all the figures can be found in the paper. The threshold 60, the threshold in 60 results in the first edges with negative curvature, a North American Europe cluster and an Asian Pacific cluster. Within the North America-Europe cluster, all intra-North America edges have positively curvature, as do all intra-Europe edges. This is an indication that Asia operates a richly connected physical infrastructure within both the North American and the European continent. On the manifold for the threshold 90, we see this time that the entire North America-Europe cluster now consists of positively curved edges. This implies the existence of rich fiber connectivity linking the two continents by means of transatlantic cables with multiple landing points. At the same time, examining the Asia-Pacific cluster at this threshold, we find that it includes now Sydney. Its intra-cluster connectivity is positively curved, but far more sparse than that of North America-Europe cluster. Importantly, we observe the presence of a single negatively curved edge between Tokyo and Quincy, Washington, shown in red. This edge connects the North America-Europe cluster with the Asia-Pacific cluster. We assess whether we are able to recover cables according to Microsoft webpage. Our inferences are validated by the map. Note that this is an updated map with prospective metros and fibers that were added after the paper as well. For example, there were no nodes in the Middle East, way less nodes in Western Europe, and single data centers in South America and Africa. We can apply similar construction for all of the cloud providers. Instead of reiterating all of the steps, we can just compare the manifold to assess the differences between the cloud providers. Each row corresponds to the manifold obtained by a cloud provider for the same threshold. We focus on a few interesting observations that we were able to make through the study of our manifolds. First, we noticed that for the same threshold, Google data centers in North America and Europe are still not connected, while Azure's and AWS are. At a larger threshold, AWS is the only cloud provider that has a direct path between Asia and Europe. This can be explained by the construction of the Bahrain data center in 2019. On the other hand, Google is the only operator to never directly connect Europe to Asia, an observation that has been confirmed by prior work. Checking on the Google Cloud page, it seems like this lack of connectivity is going to be resolved shortly, as Google is currently building infrastructure in Doha, Dammam, and Tel Aviv. AWS is the only cloud provider with connection from Sydney to North America, with very few connections to Asia compared to Microsoft and Google. This suggests a meaningful difference in the way the data centers in Sydney have been deployed between AWS and Google Microsoft. We also illustrate how the shortest path according to the manifold provides a better estimate of the latency than the one inferred by the great circle distance. More specifically, we build a linear regressor of the latency based on the great circle distance and the geodesic distance on the manifold, and compare the quality of our output for a couple of cities. Delta quantifies the difference between the real latency and our estimated. A delta close to 0 indicates a better estimate, as we can see. Delta GO beats delta GCD pretty consistently. A central strength of our model lies in its explainable output by linking the observed latency with the path taken by the data on the map. Investigating this property more in detail is an exciting prospect for us and is left as future work. The Google case also illustrates how a hole induced by the total absence of infrastructure between Western Europe and Eastern Asia can result in decreasing the quality of our prediction. We posit that this might be due to the fact that lack of infrastructure should be reflected on the true underlying manifold. In this context, forcing the learned manifold to have a hole would probably result in finding a potentially more appropriate manifold. In this presentation, we introduce a new technique to uncover topology that is based on Riemannian geometry. We build visualization that facilitates the utilization of our technique. And we compare and contrast the network of a couple of cloud providers. Thank you for your attention during this talk, and I'm now happy to take your questions.